Next topic is combination of lenses. I will start with an example. Here is an example. Two converging lenses are placed 20 centimeters apart. Um, an object is placed 60 centimeters in front of the first lens. Take f1 equal to 20 centimeters, f2 equal to 25 centimeters. So focal length is given. So basically these lenses, you can see most probably we use lenses in the cameras. Okay, and in cameras we usually use combination of lenses to two lenses. Okay, by adjusting the distance between these two, they can uh, focus image, and they can focus the image by changing the distance between those two. Now, um, I always, so the here he clearly mentioned those two are converging lenses. Sometimes they might not mention whether it is converging or diverging. We can find out that by using the f value. If you see the focal length is a negative, definitely that is diverging lens. So here he gave us both of them converging lens. Now, if you remember the lens equation, I really want you to remember this. Okay, so in this box I have a converging lens. So d naught, I always keep the object on the left side of the lens. Okay, and focal length for this converging lens is behind the lens. Okay, so that's f is right here, and image is going to be behind the lens. Okay, if that's the case, we'll end up with 1 over di plus 1 over d naught equal to 1 over f. Okay, so this is a fixed common lens equation. Now if it is a diverging lens focal length is going to be in front of the, so if you have diverging lens there, focal length is going to be in front of the lens. In that case, we'll end up with a negative 1 over f. If you have distance of image as a negative number, that means the image is in front of the lens, in the same side of the object. Okay, so those are the basic important points. Now in this example, here is a, let me erase this, so I'll have enough room. Now in this example, distance of the object, so since there are two lenses, I'm going to say d01, d02, something like that. So okay, so for the first lens, 1 over distance of object 1 plus 1 over distance of image 1 equal to 1 over f1. So f1 known, distance of the object 1 is known. So based on that, distance of image 1 equal to 1 over 20, which is focal length, minus 1 over 60, which is distance of image 1. So we end up with the distance of image 1 equal to 30 centimeters. Magnification factor is same, m1 equal to minus di by d naught, or minus, height of the image over height of the object, hi over h naught. Okay, so based on this, I end up with height of the, our magnification factor is minus 0.5. That negative indicates that the image is going to be inverted. Okay, so right here, this is the image 1, the red image. Now since you have negative m, that negative m indicates that the image is inverted. Okay, image is going to be inverted. Now the important point for lens 2 is, so the important point for lens 2 is image of first lens is same as the object of second lens. So the second lens object is image of the first lens. Okay, so d02, which is object 2, is, it's supposed to be on the left hand side of the lens. So it's supposed to be here. If it is on this side, we'll take that as positive. It's behind the lens, so that's the reason I end up taking that as negative 10 centimeters. Okay, so 1 over di2 equal to 1 over f2 minus 1 over d02, object 2. So 1 over 25 minus of 1 over 10, and with distance of image 2 as 7.14 meters. So if you have the negative number, that indicates that that's behind the lens. Magnification factor M2 is positive number, 0.714. So it is 0.714 times of the object 2R, which is also same as the image 1. Okay, so your object 2 is going to be on this side. Magnification factor, we end up with a positive number, so it is not inverted. It's on the same side. Okay, it is not inverted. But when you look at the overall magnification factor, magnification factor is M1 times M2, which is minus 0.5 times 0.714. We end up with a negative 0.357. So overall magnification factor is negative. So the final image compared to the first one is inverted. So I mean the distance of image to I'm always looking for this, and the total magnification factor I always look for this. Okay, so that's what mostly I'm looking for in this question. Now in the same question, what I'm going to do, let me move the distance of object 1 to 10 centimeters. So I'm going to do part 2. So I mean I just created this part to extend our problem. So our example, what if distance of object 1 is 1 centimeter, I mean 10 centimeters. So everything is in centimeters, so I'm not converting it to meters. Okay. So 1 over distance of object 1 plus 1 over distance of image 1 equal to 1 over f1. So 1 over distance of image 1 is nothing but f1 is 20 minus 1 over 10. That value is 1 over 20 minus 2 over 20, which is minus 1 over 20. So the distance of image 1 is, can I say this as negative 20 centimeters? Okay, so if that is the case, I'm going to redraw the diagram again. Remember, here is the axis, and there are two lenses. I'm not changing the distance between the lens. The distance between the lens is, I believe, 20 centimeters from the previous. I mean, I'm extending the previous example, so I didn't change anything other than the distance of object 1. So here is f1, f2. We know f1 equal to 20 centimeter, f2 equal to 25 centimeter. Now object 1 is right here, that is 10 centimeter. Now we end up with the image 1 as negative 20 centimeter, and the magnification factor M1 must be di1 by minus di1 by t01, which is negative of negative 20 over 10, which is 2. Magnification factor is 2. So basically the image we're going to see in front of the lens, it's going to be virtual image, and which is 20 centimeter away from the lens, and it is twice bigger than the object. So whenever you see image in front of the lens, that's called virtual image, because for the lens it's look like the object is at this point, but real object is at 10 centimeter away. Okay, now this is distance of, so magnification factor is positive, so it is upright, it is not inverted. Basically this one is distance of image 1. Now this image 1 is going to act like a object for the second lens. So this is the object for the second lens. That's how those two are, I mean their focus is going to be, I mean they're focused on. So can I take this as distance of object 2? Okay, so for the second lens, 1 over distance of object 2 plus 1 over distance of image 2 equal to 1 over f2. So I end up with 1 over distance of image 2 is nothing but 1 over 25 minus 1 over, this is 20 and 20, 40 centimeters. So I found distance of image 2 as 66.67 centimeters. So if I have the positive number, that means the image is behind the lens. Okay, so this is the front side. So left hand side is always front, right hand side is always back. So behind the lens. Now your M2 is minus di2 by di1, which is minus 66.67, which is 200 by 3 divided by di1 is 40. No, I'm sorry, this is distance of object 2. Okay, distance of object 2 is 40. Distance of image 2 over distance of object 2, which is 40, will end up with negative 1.67. So here I have a negative magnification factor. That means the image is inverted. Image is going to be inverted. Your final magnification factor is minus 3.33. That's a real image, and it is inverted, and it is 3.3 times bigger than the object. I will stop this video here. I'm going to solve the other 3 combinations also. So here I have 2 converging lens. So the next one I'm going to have converging and diverging, diverging and converging, and diverging and diverging. Thank you.